If you look around your room right now, at your keyboard or your TV remote or like that rogue Lego brick hiding on the floor, you are actually looking at the exact same material that is probably sitting on a spool right next to your 3D printer.
Yeah, it really is just hiding in plain sight.
It is, and today, well, we are finding out why. Welcome to the deep dive. We are jumping into a really fascinating article from Printara 3D. It is titled ABS Filament, Meet the Legend of 3D Printing. We are talking about the original, heavyweight champion of the desktop fabrication world.
The absolute classic.
Right. Now, if you are listening to this and you have been running your printer for, say, maybe 6 to 24 months, you have probably completely mastered PLA by now. Your prints look pristine. They stick to the bed perfectly.
You get those flawless first layers.
Exactly. But you're also probably hitting a bit of a wall when you try to make parts that, actually do real work in the real world.
That is the classic transition point for almost every single maker.
Yeah.
I mean, you start by mastering the aesthetics, right? You want the part to look totally flawless right off the build plate.
Which PLA is great for.
It is amazing for that.
Yeah.
But the moment you step into the world of functional parts, you just get hit with this massive structural reality check.
Yeah.
A part might look incredibly solid on your desk, but the physical demands of the real world, they do not care about a perfect first layer.
No, they really do not. Which brings us to our mission for this deep dive. We are going to figure out exactly why ABS was considered the uncrowned king of the hobby for so many years. We are breaking down its unique chemical properties, looking at the physics of how it handles stress, and revealing why its, notoriously challenging nature is absolutely worth mastering.
It is a total mindset shift.
We are moving beyond printing little decorative boats, right? We are stepping into the realm of real engineering here.
Yeah, because when you stop looking at your machine as just like a toy factory, and you start looking at it as a legitimate manufacturing tool, the materials you feed into it, they have to change.
So let us start with the material itself. ABS is an acronym, and I think a lot of people treat filament like it is just, one homogeneous magical plastic, like you were just melting down a candle.
Right, just a spool of generic plastic.
Exactly. But the source points out that ABS is actually this highly engineered polymer made of 3 distinct monomers. And I initially thought of this kind of like a bartender mixing a very specific cocktail, pouring 3 liquids together to get a new flavor.
I mean, the bartender analogy gets us halfway there, but it is actually a lot less about mixing liquids and much more like forging an alloy, or even pouring concrete with rebar inside of it.
Okay, concrete and rebar. I like that.
You are not just blending things. You are chemically bonding 3 entirely different molecular structures together. You want to borrow the best physical trait from each one.
And that is where the name comes from.
Right. Acrylonitrile, butadiene, and styrene, ABS. It is just a brilliant balancing act of chemistry.
So let us unpack that molecular concrete. What is that first component actually doing?
So the first one is acrylonitrile. You can think of this as your chemical and thermal shield.
Okay.
At a molecular level, acrylonitrile provides these really strong polar bonds. And that polarity makes the final plastic incredibly resistant to chemical degradation and heat.
So it is tough.
Yeah, it is the exact reason you can wipe an ABS part down with harsh cleaners, and it does not just, melt into a puddle on your workbench.
Yeah.
It provides that baseline endurance.
Okay, so that is our thermal shield. What about the butadiene? Because the source highlights this one as the real game changer for mechanical parts.
Oh, absolutely. But butadiene is essentially synthetic rubber.
Rubber.
Yes. This is the rebar inside our concrete analogy. By polymerizing synthetic rubber directly into the plastic chain, you are injecting an elastomer. So the molecules, they are capable of stretching and uncoiling when they are subjected to force.
Wow, so it actually stretches.
Microscopically, yes. It is a secret weapon that gives ABS its impact resistance. It basically acts as a microscopic shock absorber, just distributed throughout the entire part.
And then we have the styrene to finish it all up.
Right. Styrene is the concrete itself. It provides the rigid matrix. So it gives the material its overall strength, its stiffness, and it is also the specific component responsible for that hard, glossy surface finish you see on commercial products.
So we have a chemical shield from the acrylonitrile, a rubber shock absorber from the butadiene, and a rigid backbone from the styrene. When you break it down like that, you really realize how intentional the chemistry is.
It is incredibly deliberate.
But here is the non-obvious insight that the source reveals. And honestly, this completely changed how I view the spool sitting on my desk right now. This exact chemical combination is not some niche specialty material that was invented for desktop 3D printers.
Not even close. It is one of the most heavily relied upon plastics in the entire global manufacturing sector.
That is wild to think about.
Yeah, when we talk about injection molding, which is, how factories produce millions of identical plastic parts every single day, ABS is very often the default choice.
So when I am holding a spool of ABS, I am literally holding industrial infrastructure.
You are holding the exact same formulation that goes into car bumpers. Protective hard cases for power tools. The dashboard components of your actual car.
Wow.
This is the hidden industry mechanic that bridges the desktop hobby directly with the factory floor. Historically, engineers pushed so hard to bring ABS to desktop 3D printing, specifically for this reason.
To match the factories.
Exactly. If you are an engineer and you are designing, say, a custom gear for a new appliance, you need to know that your printed prototype is going to behave exactly like the mass-produced version.
Right, otherwise the test is useless.
Exactly. Prototyping with OBS means you are testing the actual end-use material.
Which means, as hobbyists, we are essentially operating a miniature industrial manufacturing plant right in our own homes. We are just using an extruder instead of a massive steel injection mold.
That is the exact perspective shift we are talking about here.
Yeah.
You have factory-grade capability sitting right next to your computer monitor.
But wait, I do have to push back here for a second.
Yeah.
Because if this stuff is so incredibly capable, why did everybody move to PLA? I mean, ABS is notorious for being an absolute nightmare to print.
It definitely earned that reputation.
Right. It requires a heated bed. It usually requires a full enclosure to keep drafts out. And it warps like crazy. The source explicitly mentions that it requires taming.
It does.
So why not just use PTG or just stick to PLA and design thicker, bulkier parts so they do not break? Like, why fight the warping at all?
That is a completely valid challenge, and it really comes down to understanding the physics of failure. Designing a thicker PLA part, it does not change the fundamental molecular bonds of the material itself.
Okay, how so?
Well, PLA is exceptionally rigid, but rigidity is a double-edged sword. Because it is so stiff, it is incredibly brittle.
Ah, I see.
When a rigid part takes a sudden physical impact, the kinetic energy just has nowhere to dissipate. The molecular bonds cannot stretch, so they just snap violently. The part shatters.
Like dropping a thick pane of glass. Making the glass thicker might make it heavier and maybe a little harder to break, but it is still fundamentally brittle glass.
Exactly. Now bring that synthetic rubber, the butadiene, back into the picture. That rubber fundamentally changes the physics of an impact.
Because it can stretch.
Yes. When an ABS part gets hit with a hammer or dropped on a concrete floor or, bolted to a machine that vibrates violently, it absorbs the kinetic energy.
So it does not just explode.
Right. The elastomer chains stretch. The material will actually yield and bend before it ever reaches the point of catastrophic failure.
So it dents or flexes instead of exploding into sharp plastic shrapnel.
Exactly.
Which makes total sense for why the source notes it is used in bicycle helmets. I mean, you absolutely do not want your helmet to shatter like a dinner plate when you take a fall.
You want it to absorb the energy to protect what is inside your head. That toughness alone totally justifies the printing difficulty for mechanical parts. But the mechanical side is really only half the story here.
Right, the heat.
Yeah, the thermal properties are where ABS completely leaves PLA in the dust.
Let us talk about that thermal reality check, because anyone who has printed functional parts has probably learned this lesson the hard way.
Oh, yeah. The classic rite of passage for a maker is the melted phone mount.
Every single time.
You spend hours calibrating your printer. You print this beautiful, perfectly custom phone mount for your car dashboard out of PLA. It looks perfect.
You are so proud of it.
You install it, you go into work, and you leave your car parked in the sun on a summer afternoon.
The greenhouse effect just takes over inside the cabin.
And when you come back to your car, your perfect functional part looks like a melted piece of modern art. It has completely drooped and dropped your phone right onto the floor mat.
And let us explain the actual mechanism there. Because PLA does not actually melt into a literal liquid puddle in a hot car. But the source points out that PLA begins to deform at temperatures around 60 degrees Celsius.
Right, it hits its glass transition temperature.
Yeah, the molecular bonds just get excited by the heat and they lose their grip on each other. The structure just gives up.
And, 60 degrees Celsius sounds high to some people. But the interior of a car sitting in direct sunlight can easily hit that temperature. PLA simply cannot hold its structural integrity under environmental heat.
But ABS can?
ABS, thanks to that Acrylon trial shield we talked about earlier, it maintains its shape, its rigidity, and its strength all the way up to temperatures approaching 100 degrees Celsius.
Which is practically the boiling point of water.
It is a massive leap in thermal endurance. This means you can confidently print parts for high heat environments. You can print custom mounts for your car engine bay. Yeah. Or enclosures for power supplies that generate their own heat. You can even print replacement parts for the heated components of the 3D printer itself. PLA would fail in minutes in those applications.
And this brings up the warping issue I mentioned earlier, because the reason ABS is so hard to print, the reason it warps and peels off the build plate, it is directly tied to those thermal properties, right?
Yes, it is the fundamental trade-off. Because ABS has such high temperature resistance, it has to be extruded at a very high temperature, but plastic shrinks as it cools.
Right.
And with ABS, the thermal contraction is significant. As your printer lays down hot layers on top of cooler layers, the top layers shrink and physically pull upwards. They act like tiny little muscles flexing, pulling the corners of your print right off the glass.
So that is exactly why you need the heated bed and the enclosure, to keep the ambient temperature high and slow down that cooling process so the layers do not shrink violently. You basically have to control the thermal environment.
You are managing the physics of contraction. It requires more effort, it requires more calibration, and better hardware. But the reward is a part that is virtually indestructible in everyday conditions.
Which gives us a very clear decision guide moment here. We want to give you a definitive framework for choosing your material going forward, based entirely on the source data.
This is crucial.
So, choose ABS if you are printing a mechanical bracket, a custom tool, or a protective case that will be subjected to drops, heavy impacts, or continuous mechanical vibrations.
Definitely.
You also absolutely choose ABS if the part will live in a high-temperature environment up to 100 degrees Celsius, like a car interior or a heated machine component. In those scenarios, fighting the warping is just the necessary price of admission for a part that actually survives.
And on the flip side of that, stick to PLA if your print will strictly remain in a climate-controlled room temperature environment.
Right, keep it simple.
Stick to PLA if you are printing a decorative statue, a board game insert, or an organizational bin that will never face sudden physical impacts or stress. If your priority is just getting a hassle-free, aesthetically perfect print without needing an enclosure, PLA is still an incredibly valid choice.
It is a deliberate choice based on the physics of the environment. But let us say you make the leap.
Okay.
You decide you need the impact toughness, you need the thermal endurance, you build the enclosure, you conquer the thermal contraction, and you get a successful ABS print off the bed.
A great feeling.
It is incredibly strong, but it still has those physical layer lines. It still visibly looks like a 3D printed object with tiny ridges all over it.
Well, yeah, fused deposition modeling is inherently a layered process. You are basically stacking hot noodles of plastic.
Right, and if ABS is the exact same material used for commercial electronics casings and pristine Lego bricks, how do we cross that final bridge? How do we get our printed parts to look like those perfectly smooth, injection-molded commercial products?
We want the strength, but not the prototype look.
Exactly. We want the industrial strength, but we do not want it to look rough.
This is where we get into, honestly, the most fascinating post-processing technique in the entire 3D printing ecosystem. And this is a highly actionable tip you can apply this week if you want to elevate your functional parts.
I love this part.
ABS possesses a truly unique chemical superpower compared to almost any other common filament, like PLA or PDTG. It is highly soluble in acetone.
Acetone, like the aggressive solvent used in heavy-duty nail polish removers and industrial paint thinners.
Exactly that stuff. But you do not just dunk your print into a bucket of liquid acetone.
That sounds like a bad idea.
That would ruin the structural integrity entirely. Because ABS is soluble in acetone, you can perform a technique called chemical vapor smoothing. You take your finished ABS print and you place it inside a sealed, controlled container.
Like a glass jar or a sealed metal bucket.
Yes, and you introduce acetone into that environment. Usually you just do this by attaching paper towels soaked in acetone to the inside of the lid. Acetone evaporates very quickly at room temperature, and the vapors are heavier than air. So these invisible chemical vapors roll down and completely envelop your 3D printed part in a vapor bath.
What is actually happening at the molecular level when those vapors hit the plastic? Like, why does it smooth the part?
The acetone vapors specifically target the styrene bonds on the very outer shell of the part. As the vapor touches the plastic, it breaks down those surface bonds. It turns the microscopic ridges of your layer lines into this self-leveling chemical slurry.
Slurry.
Yeah, the plastic essentially begins to flow into itself. The peaks of the layer lines melt down into the valleys.
It is chemically erasing the evidence of the printing process.
It really is. The vapor reaches into every tiny crevice, and the key here is timing. You only leave it in the vapor bath for a short period.
You do not want it to melt all the way through.
Exactly. Once you remove the part and let it ventilate, the acetone completely evaporates away. The styrene polymers relink, the slurry hardens, and you are left with a completely seamless, glossy surface finish.
That is just incredible. The mechanical strength of the inside remains totally intact, but the outside looks identical to a piece of plastic that just popped out of an expensive steel mold at a factory.
It looks completely professional. And the force also points out that beyond just chemical smoothing, ABS is a dream material for traditional finishing work too.
Like sanding.
Yeah. If you try to aggressively sand PLA, the friction generates heat. Because PLA has that low glass transition temperature of 60 degrees Celsius, it starts to get gummy and melt right into your sandpaper.
It ruins the part and clogs the sandpaper instantly. This is so frustrating.
But ABS handles friction beautifully. It basically turns into a fine powder when you sand it. It takes filler primer exceptionally well. And because of the chemical properties of the acrylonitrile, automotive-grade paints and spray paints bond really strongly to its surface.
So if you are engineering a custom prototype for a client presentation, or building a high-end cosplay prop that needs to look like flawless metal, ABS gives you the absolute best canvas.
It really does.
You get the rugged internal shock absorption from the rubber, the heat resistance to survive a hot summer convention from the acrylonitrile, and the ability to sand and chemically smooth the exterior until it is visually perfect.
It is the ultimate holistic package for a maker. You just have to be willing to invest the time to learn its thermal behaviors and tame that printing process.
Which is a learning curve that permanently levels up your skills. So let us pull all these threads together and summarize the ground we covered today. We started by decoding the acronym itself. We learned that ABS is not just random plastic, but a highly engineered polymer alloy.
Acrylonitrile providing the chemical shield and thermal endurance, but Acetone acting as the synthetic rubber rebar for impact toughness, and styrene delivering the rigid structural matrix.
We looked at the physics of failure. We explored why rigid PLA will violently shatter under a hammer strike, while the rubber embedded in ABS allows it to yield, stretch, and absorb kinetic energy.
We established a thermal reality check. PLA begins to deform at 60 degrees Celsius, making it totally useless for hot cars or outdoor enclosures, whereas ABS holds its structural integrity up to nearly 100 degrees Celsius.
We gave you the decision guide. Choose ABS for high-heat, high-stress mechanical environments. Stick to PLA for simple, room-temperature decorative prints. And finally, we uncovered the magic of chemical vapor smoothing. We learned how acetone vapors break down the styrene on a microscopic level to self-level the layer lines, creating a flawless, commercial-grade finish.
Taking a raw printed part and just elevating it to factory-quality aesthetics.
Mastering materials with a higher printing difficulty is not just a badge of honor for internet forums. It opens up an entirely new tier of functional utility for your machine. You are no longer limited to printing fragile desk ornaments. You can engineer brackets that hold real weight. You can build protective shells that take a beating. You can manufacture parts that live out in the heat and actually survive.
It totally expands the horizon of what you are capable of building from scratch.
Yeah. And that leads me to a final thought I want to leave you with today. We talked heavily about the hidden industry mechanic, the profound fact that the spool of ABS sitting on your desk right now is the exact same chemical formulation used by global injection molding factories to produce millions of consumer goods every single day.
It is the physical bridge between desktop prototyping and mass manufacturing.
So I want you to ponder this as you look at your printer today. Now that you know you can load the very same industrial standard material that makes up the dashboards of cars and the casings of power tools, how does that change your perspective on what that machine is actually capable of?
It makes you think.
Are you just printing trinkets as a weekend hobby? Or are you operating a miniature industrial manufacturing plant right in your own home? Think about the complex, durable mechanisms you could invent if you stopped designing fragile objects and started engineering parts built to survive the real world. Thank you for joining us on this deep dive. Go fire up that heated bed and start building.